All right, so this is the multiple choice part. We have an answer key for. This is the extended response part. So I'm going to show you some of the work. So calculate the force experienced at the yield point. So I had to estimate, this is actually not 47 psi because you have times 10 to the third, which means you move the decimal place 3 over. So if you had 47 and you moved it 3 over, it's actually 47,000 psi. And same deal here. If I trace that yield point down, it looks like about 7, but that is times 10 to the negative third, which means I move the decimal place over 3, and it becomes 0.007 inches per inches. Okay, but either way you slice it, if I'm going to find force, I need to use this formula that was handily given. And you could have found it on here too. But if I know that the stress, so this is part A, if I know that the stress is equal to force over area, and the stress is 47,000 psi, pounds per square inch, and I'm solving for force, I look up here and I see my area is 0.125 inches squared. Multiply both sides by 0.125 and you'll get force by itself. So force is 47,000 times 0.125. So it's force of 5,875 pounds. That's because the inches squared cancel with the inches squared for psi. Okay, so that was A. B is pretty similar, except even easier, because when they ask for modulus of elasticity, it doesn't say it here, but we used a crazy equation for it earlier, but you could say E is stress over strain. So here's stress at 47,000, here's strain at 0.007. So E is 47,000 psi divided by 0.007. And this should be a big number because modulus of elasticity is usually a big number. Okay, so that's 6714285, 6 million psi. Okay, so that's that one. And then the last one is find the elongation or delta. So remember, elongation, I could use this formula because I know everything else. I now know my E, I know my force, I know my original length because it was given in the problem in inches, and I know my area because I could figure that out. So let's try that out. Let's use this crazy formula. So we got E equals force times LO over area times delta. And we're looking for delta in this problem. So I'm going to plug in everything I know. 6714285, round to the nearest, 286 if we round to the nearest number. Force is 5875 pounds. Let's see, what else? Let me see if there's a quicker equation for that. Oh, yeah, let me use the faster equation. I'll do it here. 12c. Okay, I found a better equation that's already solved for delta on one of our sheets. So delta, it's going to be less work. Delta equals force times length original over area times modulus of elasticity. So in this problem, force was 5875 times original length, which was 1.75 inches. So we have pounds times inches over, and then here we have area, which you do have to, use your noggin a little bit for the area. Oh, no, it just tells you straight up, 0.125 square inches. So 0.125 inches squared times that big number from last time, the 6714286 psi. And if you do this one, you got your inches squared canceling with your inches squared, the pounds canceling with that pounds, and I'll be left with just inches, which is cool because inches would be a good way to measure how much it stretched. And when I typed all that in my calculator, I got 0.0123 inches. Now that seems like a tiny number, but we're talking about metal stretching, so we're not talking huge amounts here. So it's not uncommon to get a tiny number for that. All right, so that was the breakdown for 12. Most of these are just, crazy problems here. All right, so here's some formulas. Oh, I should have used that rather than the huge one. Okay, so we're going to do a similar thing here. It does show you where proportional limit is and where yield point is. It doesn't show you where break point is. And break point is, well, this must be like a crazy thing. Break point is where it just drops off. Usually the graph stops. Like this one, here's the break point. Okay. So here, I guess technically there's the break point stress. I don't know if this graph is supposed to be like that. Ultimate stress is the very, very highest number here. Ultimate tensile strength is the highest dot there. Okay. The break point, I don't know, I think it's right here where it just drops straight down. Let's go with that, because this shouldn't be here since it's a vertical line. So we'll call this one the break point. All right. So our numbers may be a tiny bit off from what they are in the problem or on the answer key, because it matters what you call this. So if I look at this, it looks like these go up by 50s, 300, 350, 450. Yeah, so these go up by 50s. So when I look at this, it's like, I don't know, there's 700, and that one, proportional limit, looks like it's pretty much on 700 pounds. It's important to look at your units here. So if I'm looking for stress, I'm going to use this formula here, force over area. So stress equals force over area. And in this problem, my force looks to be 700 pounds. My area is up here. Test simple has a cross-sectional area of 0.035 inches squared. And if I do that, I'll get a pounds per square inch. So whatever 700 divided by 0.035 is. So that looks like 20,000 psi is your stress. That's how much you're stressing it right there. Yield point is a tiny bit higher. I mean, to me, what's that look like? It looks like 730. So we're using the same formula. So it's the same area, and it's just a little higher pounds. So I expect a higher stress, 730 divided by 0.035. So you're really just manipulating these equations. Okay, so there's two answers. Boom, boom. Modulus of elasticity from the proportional limit. That would be, and look at this, modulus of elasticity right here is stress over strain. Problem is, we don't have stress over strain, so I might use this guy and just solve it for E. Or, if I have my formula sheet out, here it is already solved for E. Okay, so my formula for this guy is capital E equals force times length over area times elongation. Okay, so my force, we just figured that one out. That's the 20,000 psi times original length, that was the 2.5 inches, okay, over, and my area is at 0.035 inches squared. It'll cancel out with the inches squared of that, times the original length. Oh wait, not original length, how much it's stretched. Okay, now that's the new thing. Displacement is a fancy way for saying amount stretched. So if I look over here, looks like it comes right down to a nice number, 0.025 inches. All right, so a little typing later and we will get our E. Okay, so 20,000, let me pause it. Okay, so I typed it all in and I got 57,142,587 PSI. The units cancel out. And yeah, so that's pretty much where we landed with modulus of elasticity. Oh wait, that was inches over inches. Either way, we got there. Okay. So breakpoint stress, this sort of depends where you read it, but once again, stress is force over area, and this time I'm going to say 500 is my force, and my area is the 0.035 inches squared. And we'll just go 500 divided by 0.035, and that one looks like 14,285.7. That's PSI. And last but not least, the ultimate stress, which means the very highest point you see on your graph. If I were ballparking that, it looks like 775. So stress is force over area. One more time. 775 pounds over 0.035 inches squared. 775 divided by 0.035. 22,142.8 PSI. That's the most amount of stress it was able to take. Okay, so we hammered those out. You could find the strain, the stress. Didn't ask any strain things in here, but it easily could. You would just use the formula for strain, which, is, where's that? There's strain. Deformation over original length. Okay. Anyway, hope that helps. Just getting used to using these formulas and solving the problem you got. Good times. All right. Talk to you later, people. Hope that helped a little.